First, I'd like to thank the organizers for the invitation and letting me give a talk at this great opportunity. Well, today I'd like to talk about the phase transitions in the BMN matrix model, which is one-dimensional superconductor mechanics with masses. And by using multi-color simulations, what we found is two types of phase transitions. One of which is the deconfinement transition, which has been already known. And the other one is probably related with geometry. So let me show you the results. So this is the outline of my talk. I first introduced basic concepts of the BMN model and emergent geometries and so on. Then I will review the deconfinement phase transitions in the BMN matrix model. Large mass limit, the theory becomes just gauged harmonic oscillators, so it's completely easily computed. And at small mass, it's just strong coupling limit, so we can use the gravity prediction if we gauge gravity duality. Or conversely, we can use it to test the gauge gravity duality. Then I will show you our lattice simulation results, and then I will summarize this talk. Okay, let's begin with the introduction. My motivation is string theory or M theory, which is a promising candidate of the quantum theory of gravitation. But string theory is defined merely based on potential theory, so we need non-perturbative formulation to discuss non-perturbative physics, such as how field-branes can appear from the first principle, or the metric where strings embed should be derived from the theory. That kind of thing should be discussed by using non-perturbative definition. So we consider here matrix models. The basic idea is matrices should describe strings. One of the important key concepts in matrix models is emergent geometry. At large energy scale, we have just matrices. Each component are strongly correlated, so we cannot see a good information on geometry. So it's just matrices, not more than that. But at low energy scale, we would expect geometry. That means we would expect near diagonal matrices like this, which should correspond to geometry. A good example is these two spheres. These two spheres are described by the two generators, and which are near diagonal matrices. And in the larger limit, that reproduces two spheres. So that kind of thing should happen. And as we decrease the energy scale, it's natural to expect phase transition. From matrices, we would expect some phase transition to have geometry. So that's kind of one of our motivations. And as the energy scale reaches the temperature, so here we focus on the thermal BMN matrix model. Now, what is the BMN matrix model? There are many ways to derive the BMN matrix models from strings or in theory, but today I'd like to show the BMN model from membrane theory. So this is the action of membrane theory. We have non-Goto action, which is membrane area, plus potential term, which is the free-fall field. And we consider membranes on the plane wave geometry, so the matrix is written here, the flat part plus mu deformed term, plus constant free-fall here. And as in the standard procedure in string theory, we make the non-Goto action to Fourier-type action, and by fixing the gauge, we obtain this form of the action. So here we have Poisson brackets with respect to spatial two-dimensional spatial direction, and P plus is the moment, electrical momentum in the M-theory direction. And now here we have 2 plus 1 dimensional theory. Then we perform matrix realization to regularize the two-dimensional spatial part to matrices. So this is the mapping rule from the function of geometry, function of two-dimensional space to matrices, and we obtain this one-dimensional quantum mechanics. And this is the bosonic BMN model, and the full supersymmetric BMN model can be obtained from the supermemory theory. And the procedure is just the same as this discussion. So now, by rescaling this matrix X and time sigma naught, we just can rewrite that to this simpler form of the action. We have 9 bosonic matrices plus fermions, and these A, B, C directions are the SO3 part in 9 dimensions, and these M, N directions are the SO6 part. And so the symmetry is the time direction R cross SO3 cross SO6. The vacuum of the theory can be easily read from the action because the bosonic potential terms are just perfect squares. From this term, we can say that the SO6 terms are equal to 0. And from this term, we can say that the SO3 parts are proportional to SO2 generators, NA. And NA and 5 is the representation matrix of dimension N5. And we have multiplicity of this representation, which is N2. And in general, we have a direct sum of this bit. So we have now 2 types of integers, N5 and N2. And they are interpreted as numbers of N5 branes and N2 branes. This is conjectured by Mardasino, Schick, Jabari, Ramsdonk in 2002, and by analyzing the BPS spectrum. And so far, the results are consistent with this interpretation. So the BMN matrix model is as we saw, the matrix realization of supermembrane theory. So other BFSS model, we can say that this is a nonperturbative formulation of M theory. So in this context, M2 brane should be realized by fuzzy 2 spheres, and then 5 brane should be realized by the SO6 part by including quantum effects. And actually, with Goro Ishiki, the next speaker, and our collaborators, we found that a certain BPS sector realizes their geometries at strong coupling. What we did was computing eigenvalue distributions of the BPS operator phi, and by taking proper limits, we obtain S2 and S5 spherical shell distributions. So this is going to be explained by Goro Ishiki in the next talk. And another aspect is edge gravity duality. The BMN model is considered to be dual to 2s supergravity. But each vacuum in the BMN model is dual to a geometry in the 2s supergravity. And the BMN, we have, as we saw, we have 2 types of integers, and they correspond to NS5 charges and D2 charges. So the geometries are labeled by NS5 and D2 charges, and since they are quantized, the geometries are called bubbling geometries because the structure is like bubbling, quantized bubbling. And again, with Goro Ishiki and our collaborators, we found that part of Einstein equation on the gravity side was obtained by the same BPS operator phi in the BMN model. And this part is the non-trivial part of in terms of the isometry algorithm, so 3%, so 6. From this isometry, we have time direction and S2 direction and S5 direction. So we have extra 2 dimensions. And what we found is an equation of geometry in these 2 directions were equivalent to the saddle point equation in the BMN model. So we have some understanding of emergent geometries, and including other BMN-related theories, we have many insights on emergent geometries. So it's almost sure that we have emergent geometries in the BMN matrix model. Now the question is, can we see the emergence as we decrease the temperature? And so let's see for and look at phase diagrams. What we know is the deconfinement phase transition. There exists deconfinement phase transition in the BMN model. Well, at large mass limit, the theory becomes gauged harmonic oscillators. So just by doing one loop integration, we can easily obtain the free energy. So this part is the SO3 part, this part is the SO6 part, and thermodynamic part, the gauge fixing for the fourth term. So this is the free energy, and by introducing new variables, UN, we can rewrite this to this form, a summation of UN squared. So now this coefficient is the important part to determine UN so that the free energy is minimized. Now let's begin from the 0 temperature. At 0 temperature, all of the coefficients are just 1. So if they are just positive at low enough temperatures, so that UN, all of the UN are equal to 0, and the free energy equals 0. As we increase the temperature, we obtain, we hit 0 of the coefficients of n equals 1, so this one, and it becomes negative. So U1 has a finite value, so that the free energy is proportional to n squared. So this is just the transition, gross weighting transition. And the critical temperature can be read off from this coefficient, and that is U over 12 log 3. And by including higher loops, 2 loops, 3 loops, we can obtain one of our mu cubed corrections like these. And from this discussion, we can see that U1 is the important part to determine phase transition. So U1, which is the Polyakov loop, is the other parameter. Then let's move on to small mu region. At small mu, small mass, and high temperatures, the dual geometry is approximated by non-extremal black zero branes. So this is the 11-dimensional version of the black zero brane metric. And as we have, this is because the dual gauge theory is the FSS model. And since we have small mu perturbation corrections, the geometry must asymptote to the plane wave geometry with the same isometry. So this is the condition to obtain the geometry dual to the thermal BMN model. And it's very difficult, and it hasn't been solved yet completely. But by Costa, Greenspan, Penedones, and Santos obtained the geometry by doing the perturbation of mu in mu, and they assumed the simplest horizon topology, which is S1 cross S8. They obtained the geometry by also using numerical simulations. So since they have this S1 cross S8 horizon, the geometry they obtained, it corresponds to the trivial vacuum on the gauge theory side. So since we have geometry, metric, and so on, we can compute the free energy. And they computed critical temperature by computing free energy numerically. The idea is when the free energy hits 0 is the critical temperature. So, and what the value they obtained was 0.1, blah, 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 this one. Now we have the predicted phase diagram of the confinement transition. At small mu, we have gravity prediction here, and at large mu, we have perturbation in the large mu limit, this curve. And since we have bubbling geometries, many bubbling geometries at 0 temperatures, so we have we can expect other phase transitions at low temperatures, which should reflect geometrical information. Okay, so now let's look at the simulation results. Well, when it comes to computer simulations in matrix theories, we have the BFSS model, which is mu equals 0 version of the BMN model. And there are many simulations that they are intensively investigated, and the gauge gravity duality was thoroughly checked. But the BMN model, we have only one result, which has done by Simon Cottrell and his collaborator. They observed the confinement phase transition, but the phase transition, but the phase diagram wasn't completed. So that's also one of our motivation to do this BMN calculation. This is the slide to explain how we put the theory on lattice. This is explained by Danger's talk, so I don't go deeply into that. But the important thing is, as Danger said, we chose 3 gamma prescription in the Wilson master in order to maintain accuracy of the kinematical term. Okay, so this is the result of the Polyakov loop. So we can see the transition around temperature is 0.5. So, well, this is the one for n equals 11. It's not so large, but we have seen that as temperature increases, this plateau region also is going down. So this should be the confinement phase transition. And the other transition is this one. We chose the Myers term as an order parameter, and we can see the transition around temperature 0.5. And this is the transition from the trivial vacuum to a non-trivial vacuum.
Is it the first order transition or second?
Well, it seems first, yeah, the both of them should be.
Probably in weak coupling side, analytically there is analytically order of the transition should be known. So this is weak coupling, mu is large. So I think order of transition is known.
Yes.
Is it first order?
Yes, first order.
Ah, okay.
Well, this one, we don't have much more knowledge on theoretical side, but
so probably
the observation is like first order.
So probably if you make n bigger, then you see hysteresis. So here I cannot see hysteresis, but probably n is not large enough. So it looks like a second or first. It's not really clear. Maybe if you just make n bigger and bigger, probably you can see clear.
In order to see much more precise first order transition, of course we need to take the larger limit. So n equals 11 is not so large, but well, the reason why we chose smaller n is to see this type of transition, because this type of transition cannot happen in the larger limit, because and in the larger limit we don't have in the larger limit, we don't have instantons, so we cannot make transitions. So in order to see this, we need to choose n equals 8 or 11 or not so large values. Anyway, we saw two types of transitions here. And this is a typical results for in the right middle of this transition. So these blue parts are the SO3 directions, x squared of SO3 directions. And these red parts is the x squared in the SO6 directions. So we can see that SO6 directions are suppressed, whereas SO3 directions have 3 levels, and it fluctuates around among these 3 levels. So, and after the transition, we can see that it just stays at the highest level of the vacuum. So this is the phase diagram we obtained. These blue dots are the confinement phase transition, and purple points are the SO3 transition. And in the large mu limit, we saw that they are close to the theoretical curve. And actually, we have more results on large mu around and mu equals 18 or something like that. And they are just on the curve. And it seems these two transitions emerge at mu equals 2 or some values around there. So if we assume, and it was very difficult to obtain the confinement transitions at small mu. Well, and if we assume that the confinement transition goes along with the SO3 transitions, then the tendency seems to be approaching the gravity prediction. So the simulation result seems very good as a preliminary result. Okay, so let me summarize my talk. We observed two-phase transitions, the confinement one and the SO3 one. And important thing is we have to interpret the SO3 transition. So is it a transition from M5 to M2 or no geometry to S2? Because the trivial vacuum corresponds to a single M5 brane state. So we can interpret it as M5 brane, a single M5 brane to M2 brane. And actually, we saw that the SO3 directions have large values than the SO3 values. But that's not a surprise because SO3 directions, SO6 directions have a smaller mass, so by thermal effect, SO6 directions have larger values. So it's not a surprise, but we can interpret in this way as well. So it's important to discuss the interpretation as well. And in the context of gauge gravity duality, we can do furthermore. By keeping the state at the trivial vacuum x equals 0, we may get the confinement transition much closer to the gravity prediction, because the gravity prediction is the setup of the setup corresponding to the trivial vacuum. So we should do that. And yeah, I finally want to say that we can expect a richer structure at lower temperatures, and I hope to find much more emergent geometrical features in the BMN model or M theory. So let me stop here. Thank you very much.
Question, comment, David.
If one does the classical analysis, there's supposed to be a large number of vacua, which is partitions of 11. So do you see all of them, or do you just see 2 or 3 of them? So the fuzzy spheres, right, you can have them any size. So the total number of ground states is partitions of 11. But do you see all of them in the simulation, or do you see just a few?
Yeah, that kind of degeneracy should play an important role in determining levels, but there are also thermal fluctuations, and there are many states according to the thermal effect. So, well, in that session, we discussed something in order to predict from the theoretical side. But, well, from the theoretical side, we haven't obtained something.
To answer to that question, if you go back a few slides, then there was a multi-vacuum signal. Go back a bit more. This one. Next one, this one. Yeah, so those correspond to some fuzzy sphere configurations, right? So probably from the value of trace xi square over n, you can tell which representation should be more plausible.
Yes, we identified some of these states.
So at least you observed 4 different configurations here.
Actually, here we have only 3, I guess. Here and there.
Yeah, I said including trivial back. Okay, I understand. So this red is also 6 directions, sorry.
Yeah, this doesn't appear here. Well, yeah, it's just in the middle of transition.
Comment on your question. Certain fuzzy sphere configurations are thermally preferred, and that shifts as you lower the temperature. And you see here that there are, as Yuhma said, there are 3 excited. At lower temperatures, you can see many more excited. And there's also a cutoff in the number of states that are available to the system. And there are, as for small n, there are large gaps between the radii if you just plot the levels.
Right, so can you just
small n.
Can you just start the configurations in all the known vacua and evolve them?
You can, and you can end up getting stuck in them.
No, but that's exactly what I want to see, because
yeah, that's easy.
Stable phases that should be.
That's very easy, but they are not thermally preferred. They do not arise from cooling. There's we can put the system in a much larger configuration, the largest fuzzy sphere, and it won't leave it in this. It's way up there in the diagram, but it won't arise by cooling the system. So we don't view it as part of the phase diagram.
Yeah, from beginning with the 0 temperature, that kind of thing can be done. I mean, there are many lines of non-trivial vacuum, and we can see the collapses of that fuzzy spheres. But what we did was, well, I haven't said that, but what we did was by starting from the high temperatures, as Daniel says. So, yeah, then we obtained some structure.
One other comment. We do observe hysteresis between those ones. One has to go and cool the system adiabatically to go from to track the system, and one has to go very slowly to avoid hysteresis.
From higher temperature and lower temperature.
You can easily get into the wrong to one that's not thermally preferred if you're tracking this transition. And one of the constraints that you can use is the positivity of the specific heat as you lower it, to keep track that I'm in the wrong vacuum. It couldn't have got to there by cooling.
Can you go to the next slide? So here you say the 2 transitions merges at low temperature, but yeah. So here you say deconforming transition and the fuzzy sphere creation. That those temperature become the same. Is it what you say?
Actually, it's very obscure around this region for the deconfinement transition, but we saw some sign that they agree. they are equivalent to each other.
So somehow the conformant transition is related to instability of the vacuum.
Well, that's possible, but it's still not sure because this region is very difficult to obtain with conformant.
Yeah, that I agree. Yeah.
Yeah.
There is no a priori reason that these two transitions should agree. That's what I thought.
No a priori.
Is there any other question or comment? If not, let's thank you again.